Let's get more specifically into the how of chemical equations and run through some. So be able to define mole ratio. It's a conversion factor that you get when you use the coefficients of a balanced chemical equation to compare moles to moles. Be able to calculate the grams of reactants and products if you're giving a chemical equation, calculate the liters of reactants and products if given a chemical equation, also calculate, the molecules or whatever else you can do with moles. And of course, continue practicing balancing those chemical equations. So what is a mole ratio? It's a conversion factor. So we're going to make this ratio like 3 to 2 or 12 to 1 or something like that. And I want you to think these through when we're dealing with these equations. So again, what's the ratio of nitrogen to ammonia, the Haber-Bosch process that we brought up in 12.1? Yeah, that's 1 to 2. What's the ratio of hydrogen to ammonia in that same process? That's right, 3 to 2. So we can use those ratios to calculate things. And now for any equation, and you're going to want to write this down because PowerPoint and Camtasia are a little clunky when writing equations. You're going to have a given and a wanted. Now those given quantities can be in grams, they can be in moles, they can be in liters, they can be in molecules. Anything that can be converted into a mole is what you can be given. Now if you're lucky, they just give you moles. Your wanted quantities can likewise be in every different type of grams, moles, or liters. And you're using molar ratios to convert these. So let's say you have X moles of your given. And that's going to equal your B moles over your wanted divided by A moles of given. So a B to A ratio. And you use that B to A ratio, you're going to multiply your X, how many moles of given you have, multiplied by that B to A ratio. And that's going to be multiplied by your moles of wanted. So you're going to use these. So let's look about how. So how many moles of ammonia are produced when you have 0.6 moles of nitrogen reacting with hydrogen? Now, we're assuming that you have enough hydrogen. And sometimes we're going to say in an excess of hydrogen. Sometimes just assume there is enough. If there's not a given amount of hydrogen, that's fine. You're going to have given amounts of both when we're going to be calculating something called limiting reagents. But that's next. So first, identify your knowns and your unknowns. Okay, known, how much nitrogen? Unknown, how much hydrogen? We don't need that much. Unknown is how many moles of ammonia. So that's your wanting. So what's a mole ratio? So what's your mole ratio of nitrogen to ammonia? Well, that's your 1 mole of nitrogen makes 2 moles of ammonia in the presence of enough hydrogen. So it's a 2 to 1 ratio, really. So calculate this. So if you have 0.6 moles of nitrogen, how much ammonia can you get? Your 0.6 times 2 over 1 is going to equal 1.2 moles of ammonia. All right, so practice time. We're going to take this one out of your book, question 11. So aluminum reacts with oxygen to make aluminum oxide. So first off, make your balanced equation. That's right. 4 aluminum plus 3 oxygen, remember it's O2, is going to make 2 Al2O3. That's aluminum oxide. Use that crisscross method for that aluminum and oxide. If you don't know what I'm talking about, you might want to go review a little bit. So how many moles of aluminum are needed to make 3.7 moles of aluminum oxide? So your known is what you need, your 3.7. So how many moles of aluminum are needed? So you look at the molar ratio. It's going to require 4 moles of aluminum to make 2 moles of aluminum oxide. Okay, so it's a 4 to 2 ratio. So if you have 3.7 moles of aluminum oxide, it's going to require twice as many, 4 divided by 2 is 2, twice as many moles of aluminum. So you're going to need 7.4 moles of aluminum. How many moles of oxygen are needed? So take a moment. And if you balance your equation right, you saw there's a 2 to 3 ratio of aluminum oxide to oxygen. Remember, oxygen is O2. And you're going to see 5.55 moles of O2 are needed to balance that out. All right, so mass to mass calculations. All right, so how much ammonium nitrate can we make if we're given a certain mass of ammonia? And that's, how are we going to calculate that? Well, first we're going to calculate the mass of the given. And you're going to use that to change it into moles of given. Then moles of given to moles of wanted using that mole to mole ratio. So mass to moles, and then guess what? Moles to mass. And you're going to calculate out the end mass. And you're going to be doing this pretty often, especially in the next chapter. So here's the sample problem. How many grams of hydrogen are needed to make 31 grams of ammonia? Assume we have enough nitrogen gas. And that's right, you're going to end up with 31 grams of ammonia, you're going to get 5.4 grams of hydrogen. Need 5.4 grams of hydrogen. Now, other calculations you can do, of course, we've done moles to moles. You can also do volume to volume. Remember the standard temperature and pressure, you're going to do volume to volume. Once you've mastered Boyle's gas laws, you can do it at different volumes, but we're not doing that today. Particles to particles, moles to volume, basically everything that a mole can do, you can do with stoichiometry. Hooray! So some practice time, just going to go over the questions and I'm going to read out the answers. I'll pause. You should pause rather. So for your sample problem 12.6, you have nitrogen monoxide and oxygen gas, remember O2, are going to react to make nitrogen dioxide. So balance out that equation. How many liters of nitrogen dioxide are produced when 34 liters of oxygen react with an excess of nitrogen monoxide? So assume standard temperature and pressure. And that's right, you're going to get 34 liters of oxygen will make 68 liters of nitrogen. It's a nitrogen dioxide. It's a 1-to-2 ratio. And solid phosphorus, P4, and hydrogen gas can be combined to form phosphine gas, your pH 3. How many liters of phosphine gas are produced when you have 0.42 liters of hydrogen and an excess amount of phosphorus? And that'd be 0.279 liters of phosphine gas. Now, this is a complex equation that we're going to do in class, and I encourage you, if you really feel like you're doing really well, to try to actually do this stoichiometry equation. Now, I'm not going to write the equation down in here. You got to come to class. I'll give you the answer, and you might have to go back and really figure out what's going on. So there are, if you have sodium azide, it's NaN3. That's in airbags, and it decomposes to make sodium metal, which is, of course, a liquid metal and highly reactive, and nitrogen gas. Now, that sodium metal is going to react with potassium nitrate to make potassium oxide, sodium oxide, and a little bit more nitrogen gas. This gets rid of that highly reactive sodium, which you don't want in an airbag. So balance both reactions. This will take you a little while. The number 10 is going to come up. How many liters of nitrogen gas are produced when 130.06 grams of sodium azide decomposes? Fun fact, that's how many grams are actually in an airbag, and it just so happens to be 2 moles of sodium azide. So that's handy. So how many liters of N2 are made? Well, hopefully you figured it out. It's 69.44 liters of nitrogen gas. 3 moles of nitrogen gas, N2, are made in the first reaction and 0.2 moles in the second reaction. You can check your math and find out that it's a complicated equation, but you can do it.